Welcome to class number 10, at least it's class 10 this time around. This is the lecture on lighting. Part 1, we'll talk about the Phong lighting model. Before we talk specifically about what Phong means, let's just talk about some simplified models of how light works in general. The reality is light is extremely complex as it comes from a light source and then it bounces off of different objects, and it can bounce, it can reflect, it can refract, it can do all kinds of different very complicated things. So in order to calculate lighting for our scenes, we're going to need to simplify what we model the light as. So here we are sort of in order of increasing complexity. The simplest thing we can do is to model what we call ambient light. Now, ambient light is the light that just sort of fills everything. We will model that mathematically as just an add. We will just add a certain amount of light to every surface in every direction. Ambient light has no preferred direction. It has no preferred location. There's a color we'll assign and we'll add that much light. Now, what we're modeling here is actually the most complicated thing to model, and that's probably why we've used the most simplistic form of modeling it. We are modeling bounced light. It says here, bounced light. What does that mean? Indirect light. For example, you can do this yourself. I have overhead lights above me. I have no light sources below me. But when I hold my hand like this, and you can even see it there on the camera, if I tilt it toward the camera a little bit, the bottom of my hand is blocked from the overhead lights. There is no direct light hitting my hand there. And yet, my hand is not black. If I didn't have a fill light is to counterbalance the direct light. Like when you light a subject, you will shine a light on that subject, and then you'll probably put in a fill light to fill in the back side so it doesn't look black in the back. And we'll use ambient as our fallback for that. One more thing about ambient. Lighting artists do not like ambient because it's very unrealistic. It's very unrealistic to imagine that the amount of light bouncing around the room is the same everywhere. So a lighting artist would prefer to use fill lights, to put light sources, to just fill the room with light sources that represent the light bouncing. That's what they'd like to do. And so there's a give and take there between the mathematical simplicity of simply adding ambient versus the more realistic approach of having a million different little light sources. Okay, so that's ambient. Next up on the complexity tree is the directional light. Okay, a directional light does have direction, but does not have location. All right, we would use this for example, the sun. The sun is very, very far away. If we're doing a game based on, like on Earth, the sun being 93 million miles away is approximately the same distance on the ground as it is on the 10th story of the building. It doesn't really matter where you are. The distance fall off is going to be the same. And the angle, if I run a mile, in my game, I run a mile, the angle from me to the sun is slightly different, but it is so tiny that we can easily approximate that as parallel. So what we'll do is we'll say for a directional light, the light has a direction and it is moving parallel. And also it will not have a location, so it doesn't change with distance. We won't have it get dimmer as you get farther away from the light source. So that is a directional light. Next up on the complexity scale is the point light source. This is probably the most realistic way to model a light source, but it assumes that your light source is very, very tiny. Here we assume that the light source is a point, physical point in space, and that light radiates outward from that point in all directions. So the direction of the light will come down to a very quick vector subtraction. You take, your location, say I'm right here, then the direction the light comes to me is from the light there, like so. Okay, so like my example here is a candle. You're in the spooky horror game and you're carrying the candle around. The candle will radiate light in all directions, and it will probably have a distance fall off, so that when I'm near the things near the candle are brighter. As you get farther away, things get all dark and gloomy in the distance. And then we couldn't have a horror game without a flashlight. So with a flashlight, we take that point light source idea again, so that it comes out at an angle, has a distance fall off, but then we also clamp the angles on the sides here. So we'll say like there's a cone of light that comes out. All right, so that's a spotlight. What we're going to do in our labs, we're going to have point light sources in the lab and an ambient source in the lab, and be on the lookout for the directional light to show its head during some exercises, some in-class exercises, and maybe some exams. Okay, now that I've said that, let's talk about the Phong lighting model. The Phong lighting model, now that we talked about the different kinds of lights that we can model, how the light comes into the surface, how does that reflect off of the surface and then affect the color of that surface. So ambient. I mentioned ambient before. Ambient is just going to be a flat add. It doesn't care what the normal of the surface is. It doesn't care how reflective the surface is. Just add a certain amount. And so that's what we'll do. We'll just add a certain amount for ambient to make it not completely black. Okay, what is the diffuse term? The diffuse term is the concept that, like I was doing with my hand, if I point my hand at the light source, it's very bright. And then as I tilt away, now it's not as bright. And then now I'm in shadow, right? So the angle of the normal of the surface towards the light source will determine how bright the reflected light is. It's pointed at the light source. If the normal of my surface is pointed right at the light source, very bright. As I make it less towards, so now the normal of my surface is pointing this way, the light source is up here, it's not as bright. And then once I get to 90 degrees, you can even see the shadow of my hand coming across. Now I'm in shadow and I don't get any contribution from that light anymore. Okay, so that is diffuse. And with all of these angles that I'm describing here, it shouldn't surprise you that the diffuse part is a dot product. After all, it's always a dot product, right? Okay, so that's a diffuse surface. But what it doesn't cover is a shiny surface. The next term is the specular term. And what the specular term represents is the shininess of the object. And it's definitely hard to see just from this diagram right here, but these are just the little shiny bits that are reflecting the light. You can see it better when you look at the combination image, and you see that these highlights are in fact these little bright spots on the image that make it look glossy. Here's an example. I went and got one of these controllers, and you can see, because I like this because it highlights both types of materials. The ring here is a sort of satiny kind of material that is, it has very diffuse highlights. So it's brighter here, but it's not really reflective. But the buttons, let's show a button here. This button, as I move it around, you can see that it catches the light and it looks very shiny and glossy. Here, this button, get it closer. Very glossy and shiny because it's catching the highlights from the light sources. whereas the material around it doesn't really catch those as strong, right? Okay, so that is what a specular reflection is, and by attenuating the amount of specular versus the amount of diffuse, we can make the material either look very, very not shiny, right? This is very matte or not shiny, and then we add in the specular, and now we have a very shiny looking shape. Okay, so that is Phong lighting. The idea of Phong lighting is to combine all three of these terms, and I'll show you what the mathematical model is for that in just a moment to get the overall lighting. All right, so we talked about the Phong lighting has those three contributions: ambient, diffuse, and specular. The ambient lighting was mathematically just extremely simple. It's just an add. You just add an amount. Okay, diffuse. The diffuse I mentioned was going to be a dot product. So we will typically model the diffuse contribution to the Phong lighting simply with this dot product. And here I have the equation here. C represents the color of the light source. N is the normal of the surface. And L is a vector pointing from the object, from the surface back towards the light. Now, sometimes it makes sense to describe L maybe pointing from the light to the surface, but just to drop the minus sign, we want this to be positive, right? When the normal of the surface is pointing sort of more or less towards the light source, that would be a positive lighting contribution. And so just to keep that positive, my diagrams, I have the L vector defined as the direction to the light. Okay, so there's your equation. This is the color of the light source, a non-normalized vector, and then n dot L, these are normalized vectors. Note, the color of the light source can include the brightness of the light source. A bright white, a maximum white light might be 111. A very dim white light, like a dark gray light, would be 0.1, 0.1, 0.1. And remember that if the light source has a distance fall off, then it will be bright when you're close to the light source and dim when you're far away. So you might need to attenuate this C vector, or have a distance fall off active on this C vector. So what do we say here? The light comes in from here. It is reflected and scattered in all directions off of that surface, and the amount of light hitting that surface is proportional to this dot product. That's the lighting contribution on that surface. Now, how much light is reflected off the surface may depend on the color of the material. If the material is a white material, then it will reflect all the colors of light that hit it. If it is a red material, it will reflect mostly the red colors that come off it. The next contribution was the specular contribution. And here's the equation for that. Once again, we have the incoming color vector. Now, I'm running that as a vector. That's not XYZ, that is red, green, blue, RGB. But we can just put this three contributions just like a 3D vector, so we'll do it mathematically as a 3D vector. Okay, again, we have a dot product of R and V, and then this is raised to a power. Let's take a look at what those are. Here's that same diagram where we have light. The L is the vector back towards the light, N is the normal. What are R and V? Well, R is the reflected vector. If we imagine the light coming this way, and think back to the Phong lab, the angle of incidence equals the angle of reflection. This angle equals this angle. So we'll use the L, we'll use the N to calculate what is R. R is that vector. The R is the angle at which you get the brightest maximum reflection. So what is V then? V is the angle, or the vector I should say, towards the viewer or towards the camera. You have the camera sitting up here, this eyeball sitting up here, it's looking at the pixel there. So what is this angle between the brightest return and the angle you're looking at? We're going to do a dot product there so that if the R and the V are parallel, that would mean you're looking right down the reflection. You're looking at the reflection of this brightness. And if they get far apart, like if they're 90 degrees off, then that means none of that reflection is coming at you, right? So the dot product would be 0. We take that and then we raise it to a power. The greater the power, the sharper that highlight is going to be. So if we want a very specular, glossy surface, we will have a high gamma. We will have a very high power factor there. If we want not a shiny surface, just like a matte surface or a satiny surface, we will have a lower value for the gamma. And once again, that is the color of the light being reflected off the surface, and we will multiply that times the color of the material to say how much actually is reflected. Okay, so that's the breakdown of our lighting models. We talked about the breakdown of Phong into ambient, diffuse, and specular, that we'll add those up. That diffuse is just a dot product. The specular is calculating some angles, doing a dot product, and raising that to a power. And ambient, of course, just you add it in. We combine those together, and that's the Phong model of lighting. We also talked about modeling light sources in different ways. We might have just an ambient light that fills the room, or directional light that just it has a uniform direction, a point light source that radiates out in all directions, and of course the ever popular spotlight. Can't have your spooky, gloomy horror game without a flashlight. In part 2, we're going to come back and we're going to talk about how the light reflects off the materials. I mentioned we're going to be multiplying by the color of the material. Let's look into that in some more detail in the next set.